Look at the modern European Alps. You see a vibrant, forested landscape framed by walls of jagged stone and snow. But the steep ridges and deep valleys are not permanent fixtures. They are the physical scars left behind by a creeping blanket of ice. For the last 2.5 million years, an era known as the Pleistocene Epoch, the planet oscillated between extended, brutal deep freezes and brief, warmer thaws. Understanding this cycle of glaciation shifts how we look at the Alps. We are not looking at a static geological postcard, but rather a physical record of Earth's volatile climate history. The mechanism driving these massive temperature swings is celestial. Slight shifts in Earth's orbit and the tilt of its axis change the amount of solar radiation hitting the northern hemisphere, forcing global cycles of cooling and warming, known as Milankovitch cycles.
In the early 1900s, geologists Albrecht Penck and Eduard Bruckner mapped exactly how this orbital engine physically reshaped Central Europe. This chart shows the timeline they constructed. By tracking layers of ancient gravel deposited in river terraces, they identified 4 distinct advances of the ice sheets. They named these cold periods alphabetically: Gunz, Mindel, Riss, and Würm, after the Bavarian rivers where glacial debris was thickest. This 4-part timeline became the foundation for all modern quaternary geology across the continent. The Gunz glaciation began roughly 1 million years ago. During this window, the planet's orbital rhythm shifted, locking Earth into extreme 100,000-year deep freeze cycles. As the Gunz ice sheets thickened and pressed outward from the high peaks, they initiated the violent carving of Europe's major river networks. Around 450,000 years ago, the Mindel glaciation brought another massive expansion. Millions of tons of ice flowed down the established channels, grinding heavily against the bedrock. When a glacier advances, it acts like a slow-motion bulldozer, scraping up rock and leaving behind a structural mass of debris, a moraine. Its sheer weight scours out the terrain, grinding a narrow, V-shaped river gorge into a broad, U-shaped valley. Through these repetitive gouging actions, the Gunz and Mindel periods established the macro-architecture of the Alps, carving the wide, interconnected valley networks that direct the flow of Europe's major rivers today. The third major advance, the Riss glaciation, was the most extensive. Ice sheets pushed out of the mountains and spread deep into the Bavarian and Austrian forelands. Geologists track the massive scale of this expansion by observing distinct parallel scratches, glacial striations, gouged into bedrock miles away from the modern snowline. The final freeze in the classical framework is the Würm glaciation. It turned Central Europe into a freezing, arid steppe, dominated by cold-adapted megafauna like the woolly mammoth. Because the Würm is the most recent cold period, its geological footprint is highly visible today. Thick layers of fine, wind-blown dust, known as loess, created by glacial grinding, still blanket much of the continent. As the permafrost line crept southward, human populations living in Europe had to adapt. Facing dropping temperatures, Neanderthals secured dense, high-calorie food sources to survive the extreme cold. They utilized specialized Mousterian stone tools, carefully flaked from flint, to hunt massive herbivores migrating across the tundra. As the ice continued its march, conditions worsened. Human populations were forced to migrate into southern European climate refugia, waiting out the deep freeze. When Homo sapiens arrived in Europe later, they navigated the exact same glacial corridors and wide valleys left behind by the slowly retreating ice. The Riss and Würm glaciations acted as an evolutionary crucible, testing human resilience and dictating migration patterns across the continent. Penck's 4-stage terrestrial model stood for decades, yet to measure the exact severity and timing of the ice ages, scientists eventually had to look offland and drill into the ocean floor. By extracting sediment cores, researchers measure oxygen isotopes trapped in microscopic shells, creating marine isotope stages, a high-resolution temperature record. This ocean data reveals a complex history, documenting dozens of distinct glacial pulses over the Pleistocene. The classical Gunz, Mindel, Riss, and Würm still hold up. They map directly onto the largest, most severe clusters of deep freezes found in the oceanic record. The deep sea cores validated the early fieldwork. They proved that the massive ice sheets observed in the Alps were localized expressions of a synchronized planetary rhythm. Around 11,700 years ago,
the worm glaciers retreated. The planet transitioned into the Holocene, the relatively warm interglacial epoch we live in today. The lush, accessible alpine valleys we traverse today are currently in a state of temporary thaw, resting between the inevitable swings of Earth's orbital cycles. Establishing this deep time baseline of natural climate variation is critical. It provides scientists with the exact metrics needed to isolate and measure modern human-driven warming. The history of the Alpine glaciations is a physical reminder that Earth's climate is a powerful, dynamic engine, one that has dictated the shape of geography and the survival of species before, and will inevitably do so again.